So today we're going to talk about the last pieces of the phase diagram. We're going to get all the way down into the coldest region on our TX phase diagram where it turns to solid. I also have a few interesting liquid phase diagrams on here. We talked last time about the upper consolid or upper critical solution temperature, above which the solution is homogeneous, below which you have the possibility of being heterogeneous. If you're on either end, like really concentrated, like dirty solvent, on either component A or component B, it's probably going to be miscible. I'm sorry, probably going to be homogeneous. Um, but there'll be some concentrations in the middle where it splits into two layers. And now we're going to see the possibility of having a lower consolid solution temperature. Now, solution is the word we give to anything homogeneous. So we actually have today, we're talking about solid solutions. So like this key is a solution. Kind of strange. It's a homogeneous mixture of copper and zinc, brass. Okay, aluminum alloys. That's a solution. Okay, homogeneous mixture of aluminum and uh, titanium and silicon and different kinds of metals that put together, and they blend those alloy solutions to get the properties that they want. So it's a fantastic area of science. Now this is a solution of. This is the phase separation in metal with hydrogen diffusing into the metal. So this is another problem for the hydrogen economy, essentially that hydrogen can embrittle metal. So if we're storing hydrogen in a metal container, the hydrogen can make the metal container brittle, and that's not what we want. Okay, and so this is an example of palladium. This is the phase diagram of hydrogen and palladium. And so over here we have a few atoms roaming around in the palladium metal, but then over here we have a highly hydrided phase of palladium. When you have this situation, the metal is no longer as flexible as it needs to be, and you can get ruptures and cracks. Okay. Now this over here can't really be accurate because this is 75% hydrogen and a few palladium atoms moving around, and I don't know what happens like to this side of this. It looks like it's a homogeneous solution here, but yeah, I don't know. So, but this is an example of a palladium metal exposed to hydrogen for a period of time where it becomes hydrided, and the solution is to bake it out. Hydrogen is going to be mobile, and so you turn the heat up and bake that metal, and you can drive the hydrogen out of it. This is the time to fracture. So you've got metal, and mechanical engineers are great. I love their research. So they'll have a particular structure and they just pull on it till it breaks or push on it till it breaks. So they're always breaking stuff. Okay. And so this is a time to fracture, and it's a log scale. So, highly hydrated in like 0.1 hours, it fractured, and that was with a half-hour bake time. They go to 3 hours, and then they get up to 1 hour bake time, fracture time. 12 hours, they're getting close to 10 hours before it breaks, and so on. So this is just showing you that you can drive that hydrogen back out of the metal. Now, radioactive metals, you can get, it's not really hydrogen, but you can get some strange behavior too with radioactive metals because helium, so radioactive metals produce alpha particles, many of them, and then you have helium, a potential helium embrittlement or helium contamination in the metal because the alpha particle, when it comes out of the nucleus, is a helium nucleus, and it will collect its electrons, and then you have a helium atom floating around inside the metal structure, and so changes the properties a little bit. Okay, then we can have lower solution critical solution temperatures. So this is really strange. This is a mixture of triethylamine and water. So this is pure triethylamine over here on the right, pure water over on the left. You see again, homogeneous if you're on either side of that, heterogeneous in the middle. Below the lower critical solution temperature or lower constant temperature, it's miscible. So miscible means that there's no phase separation at any concentration. When you get above that temperature, it's not miscible. You have regions where it's homogeneous, over on the left, over on the right. But if you're in the middle concentrations, then it's heterogeneous. You have two layers. Now, this is a great example of a molecule that we have, remember in the calculating the heat capacity, we had active vibrations and inactive vibrations. Remember that? And so below us, this temperature, we have the ability for hydrogen bonding. So that nitrogen's got two lone pairs. A hydrogen bonding of water can come in and associate with that molecule and help keep it in solution below this temperature. So why would it go heterogeneous above a certain temperature? Think about those arms on the triethylene. That's a very low frequency vibration. You're moving lots of mass, and there's not a strong restoring force. There's not a strong spring constant to that motion. And so this ethylamine molecule is sitting out there with these arms that aren't moving very much because there's not enough temperature. But you start raising the temperature of the mixture, and now these arms move around and they keep water from hydrogen bonding to the nitrogen. So above a certain temperature, you actually lose the ability to have those hydrogen bonds that stabilize this solution, and then you get phase separation. Many of these will turn around on the top if they don't boil. Some of these boil before they turn back around on the top, but we might have an upper solution, critical solution temperature up here. It may just go up here and then you have the vapor curves, or it may turn around and become miscible again with an upper critical solution temperature, TUC. And what's happening there is now water is losing some of its ability to hydrogen bond to itself, right? You give water enough temperature, you get it up to 100 C, and it loses all the ability to hydrogen bond to itself, and it becomes a vapor, okay? But in a mixture, you might have this upper critical solution temperature when water starts to not care what it's around. Most of the time, things separate in water because water likes water more than it likes anything else. It hydrogen bonds. Each water molecule can hydrogen bond to 4 other water molecules. It can donate hydrogens to 2 others, and it can receive donations from 2 others from the lone pairs. So those are 4 associations that are highly energetic. So water loves water. And if you raise the temperature enough to where water doesn't really care, then you get a homogeneous solution. You get below that temperature, water excludes everything else. And so then you get phase separation. But down below, like in this case, when the substance itself can hydrogen bond with water, you get below that temperature now that can form hydrogen bonds with the solute, and you can get homogeneous again. Here's that exact example in nicotine. So nicotine has 2 temperatures here. It's got the lower critical solution temperature and the upper for that very reason. Now we get into distillation of partially miscible liquids. So this is what we've been covering so far. We have we have an azeotrope. Can you tell me which this is? Is it you have 2 options. Is it a low boiler or a high boiler? On the count of 3, low or high? 1, 2, 3. Very good. It's the lowest boiling point, right? You see that here. This is the azeotropic boiling point. Okay, and then it's homogeneous and miscible in this region right here. Okay, and then down below it's heterogeneous. Okay. Now, sometimes this upper critical solution temperature doesn't exist because it starts to boil. So notice this region right here, from here up, it's boiling. How do I know that? Well, because I've got this vapor curve. So I'm in equilibrium with the vapor. And so we've got this vapor liquid equilibrium region. We could say we would call it the boiling point if this was at the pressure of 1 atmosphere, then those would all be boiling. But they all have some vapor pressure, but this would be the vapor liquid equilibrium region. And so we would say from that point there up. So this isn't really an upper critical solution temperature because it doesn't go homogeneous. Okay, it's homogeneous on the left and the right, but in this middle region, it's heterogeneous. Right? When we say phase, there's a number of phases is equal to 2, that's heterogeneous. Up here too, it's also heterogeneous because you've got a vapor phase and a liquid phase in equilibrium with each other. If you're over here, it's all liquid. If you're up here, it's all vapor. So I should be able to drop you anywhere in these phase diagrams, and you should be able to know what phase you're dealing with or whether you have 2 phases in equilibrium. Okay. Now, this is a little bit of a complicated situation in terms of looking at it in the lab. So let's put your round bottom flask here. So you got vapor, and you got layer 1 and layer 2. And the whole thing's boiling. Okay, it's a little strange, so if you're right here, you've got an equilibrium between this sort of eutectic vapor and this composition of layer 1 and this composition of layer 2. So you got 3 phases in equilibrium at what we call this eutectic. So if we were to do the lever rule, which I don't think I've ever even done a 3-component lever rule, but you've got the fulcrum here, and you've got a big kid over here sitting on the seesaw, okay? A tiny little kid right here, and an even smaller kid. So the number of moles of A in this case, because B is over here to the right. So this is B. So you've got a lot of the liquid phase B, layer B, a little bit of vapor, and even smaller amount of the liquid phase A. So this whole region contains 2 phases. Below that dip, so like below this point, it's just liquid phase A and B in equilibrium with each other. Above this little point, you have boiling. So you've got vapor liquid equilibrium above that region. But I thought since it's spring, you look at this and it looks like a familiar object. You've got 2 eyes there and the 2 ears and a little nose. And so we're getting close to Easter. So that's it. I'll call that my bunny phase diagram. Okay. Now, distillation of these things is really kind of a confusing thing. If we were to take a homogeneous solution A and put that in the still bottom, what would happen? So you should be able to walk through this little path. We bring it up here, it would boil at this point. Is everybody okay with that? You raise the temperature, it goes up. When it hits that black line, it starts to boil. Not a problem. We've done that before. And then what's collected? Let's do just a simple distillation. So a single step. Simple distillation means that the vapor is concentrated, and this is B down here on the x-axis, so the vapor is concentrated in A. A has the lower boiling point, so it's the more volatile substance. Okay. A simple distillation is just one step. So then down here we're at B2. As the temperature is cooling, as it goes over through the condenser and into the collection flask, it's homogeneous. So if you were able to look at the condenser as the temperature is dropping and saw this data point B2, it would be a single phase of liquid. It drops down into the collection flask. It's now cooled, and we end up with the lever rule problem and 2 liquid phases. So here's our fulcrum, and we've got a big mass here, a whole bunch of liquid layer B, and a tiny amount of liquid layer A. So it's weird, isn't it? You have a homogeneous still, you do a distillation, and you look in the collection flask, and it's 2 layers. That's kind of strange. You would expect it to be pure or something, right? You just distilled this, and it's not. I mean, it's enriched in A to the point where it becomes heterogeneous. Nature's a tough old bird. It does weird things. Okay. So so we've already talked about this, that eutectic mixture is the minimum boiling point. So now let's cool it down further. So we'll go down below the liquid layers and we'll start to solidify things. So let's start at this point A1 here. And you look at the phase diagram, you can see that it's liquid and it's one phase. So it's homogeneous. Oops. I don't have my erasers. Homogeneous. And we start to cool it down. Okay. So over on the far left is pure A, and over on the far right is pure B. Now what I've done for you is I've color coded this. So up here at the top, it's not that pure blue color because it's got a little bit of the yellow pure A in it, but it's a mixture of liquid A and liquid B. So if I were to ask you describe the system at point A1, that's what you would choose, liquid A and liquid B. Does everybody see that it's a liquid homogeneous mixture? Okay. Then we cool it down and we hit point A2. And what happens? Well, when we were doing condensation from the vapors, we were getting liquid drops. Now we're in liquid and we're going to get precipitation. So we cool it down and pure B starts to precipitate. So you see that little crystal of B. A little chunk, a little nucleation center starts to grow. We have a cold temperature and B starts to form and it's solid B. But we don't just have liquid A, we still have liquid A and liquid B up in, surrounding the solid. Does that make sense? Because we haven't precipitated all of the excess B out. So, no, it's heterogeneous now. So since we have two phases, we're looking at solid phase. Now the liquid up here is still homogeneous, but it's a homogeneous liquid surrounding the solid, but the whole system we would call heterogeneous because we have precipitation. We have two phases involved, so it's heterogeneous. Okay, and so in this case here, you see this, this is solid, two phases, but this is two phases because you got a liquid and you've got B. So it becomes heterogeneous. Anywhere below that blue curve, this liquid curve here is the barrier where it becomes heterogeneous. Let's keep cooling it down. We get to point A3. And all this heterogeneous region, we're looking at this is ZB, right? That's the composition in this whole phase diagram. We're following it down. So we're going down in temperature, staying at ZB overall composition. Okay. And so when we get to A3, here's our fulcrum. And we would do the lever rule. We have about equal masses or equal moles in the liquid phase and in the solid phase. So we still have A liquid and B liquid. That's the composition over here. So this right here is the amount of A liquid plus B liquid. And what's the composition of that liquid layer? You just come down here and look at the x-axis, right? So it's about 60% B and 40% A. Does that make sense? So you're following that blue line down, and that's the composition of the liquid. Does it make sense? Yes. If we're moving down in temperature, the liquid becomes more concentrated in A because we're precipitating out the B. Everybody see that? That's an important point to recognize. As B gets removed from the liquid starts to move towards A because we're precipitating out the B. Then we get to E, or A4, where we have this, if this is our fulcrum, now we have three phases in equilibrium. We start to form some A. So we're forming some B. We still have this liquid, this eutectic of A liquid and B liquid. And then this is the first point. Once we go below this point, then we're going to start forming some liquid, solid A. So let's go down to A5. And now the color is really coming. Notice how I've tried my best. This is a dark blue. And as we remove the pure blue color, it gets more green, which is blue plus yellow. And then once we get below E, the outside part is solid A, and the big crystals are solid B at A5. And we use the lever rule to determine, like we have a lot of pure B and we have a very little of pure A. And I chose these colors because this is a great micrograph of Inconel 718. It's a nickel a nickel super alloy. And so you have the nickel, and then you've got this mixture of nickel and whatever it's alloyed with as far as the yellow. So it's mostly B and a little bit of A holding it together. Now that's the part of the material science is you might want to have a metal that's very strong under compression, so you can't crush it, okay? But it needs to have some flexibility so it doesn't fracture. And so we might have a really strong phase B, a good compressive strength, but then you put a spongy metal in the yellow region to allow it to flex a little bit. And that's what a material scientist does, is they try to find these alloys that have the right tensile strength, the right compressive strength, the right shear strength. Shear is when the planes are moving this way. Compression is when they're smashing together, and tension is when they're being pulled apart. So this, I really want to make sure I answer your questions on this one. This is a very new one. Can you go in reverse? We start here and start to warm it up. If we put a point here, anywhere we drop a point, you need to go right and left. If you're in a two-phase region, you go right and left and draw your lines, and that's the seesaw that's in equilibrium between those two phases. If I drop you right here, you go right and left and you stop at the line that you hit. So you come over here and you stop there. What line is that? That's pure B. And then you go left and hit that. What line is that? That's the liquid composition. So if you were come down here, you'd see it was 60% B and 40% A. So no matter where I drop you in here, you should be able to go right and left and talk about the phases that are in equilibrium. If it's above this blue curve, yes, it's a module. Yeah. And then you might in the liquid have some partial miscibility. You know, you might have a lower critical temperature and upper where you'd have that ring. You'd have heterogeneous inside the ring, outside the ring, homogeneous. But that whole region would be what we would call partially miscible. Yeah. And then below that ring, you would have miscible, homogeneous liquid. Above it, you'd have miscible, homogeneous liquid. And then you get into the boiling lines. And you may or may not have an azeotrope. So that's everything really for our composition binary mixtures. So this is the temperature curves. If we were looking at that A1 through A5, this is what happens to the temperature as you cool it down. So as we go from A1 to A2, we're just cooling the liquid. And liquid, solids, gases, we know this, they have different heat capacities. So we pull a certain amount of energy and the temperature falls at a particular slope. It's the slope of that energy with respect to temperature curve, okay? And so that's the heat capacity, the slope of that line. So the liquid has a particular heat capacity. It seems to be small because we pull a little bit of energy out and the temperature drops pretty fast. Then we get to the solid where B is starting to precipitate. And then we have this heat capacity of this mixture of liquid A and B plus the B solid. And so then we cool down here. We get to A3, we're cooling it down, we're precipitating out the B, we still have A liquid and B liquid. And then we get to A4 where that eutectic is forming, and we get a pause. And we have three phases in equilibrium. We're starting to form, I don't show it on here because it'd be too small, but we're starting to form some pure A. And that's three phases in equilibrium, and we'll do that until all the liquid disappears. So once we get past that eutectic, all the liquid is gone, and we're now cooling this solid that contains just A solid and B solid. So anything above the eutectic has some liquid, anything below it has only solid. Now let's add one layer of complication. What if we have molecules that form? So, you know, you might have, I think the one I have, I think it's calcium silicon. So we could form like bimetallic compounds at various ratios. And so let's say we have solid A and solid B, and we also have another substance, solid C. How would we determine if C was its own substance? Right? If you've got let's say you've got a mixture of silicon and aluminum. Okay, so you could have pure silicon over here, pure aluminum over here. How would we know if there was like a compound that was 2 atoms of silicon and 1 atom of aluminum? How would we know that? The way we would know that is if it has its own melting point, right? And so look at this curve up at the top. That liquid line above this eutectic is where we start to see melting. Okay, and if we follow this line C, it goes up, it's a solid all the way to the top until it melts. Okay, so this is the melting point. T melt for C. This is T melt for A. Can I just put an M for T melt? Okay. And this is the T melt for B. So we have 3 melting points on this diagram. So that means that we have 3 substances, not just 2. Okay. Now, if this C is right in the middle, then C is the compound AB. So it's 1 mole of A and 1 mole of B because it's right at 50%. But it doesn't have to be. It could be off to like 2 to 1, 1 to 2. It could be, any kind of whole number ratio. So that's pure A, that's pure B, and this is pure C. If we're on a line, we don't have to do the lever rule. So if we're on that C line, we go all the way to the top and it melts. Okay, so that's an important point. So here we are at A1, and we're going to cool this liquid down. What happens when we hit that line? We don't form pure A, we form pure C. So pure C starts to precipitate out. And we keep going. We get to A4, we're at that eutectic pause, and we'll sit there until all the liquid precipitates out, and then we've got 2 phases in equilibrium, green C and blue B, because we're on the B-rich side of C. If we were over on this side, then we get down here and we'd have A solid plus C solid. Does that make sense? We're over on the left, we're on the right. We have different end results, but notice if I drop you right here on this phase diagram, what did I say? You're in a heterogeneous spot. You've got 2 phases. And so you draw your tie lines to the right and to the left, and you stop when you hit an interface. So this right here is about 50% of moles of B and 50% moles of C. We don't have A. We don't go all the way past that to hit the 3rd line. We just have 2 phases in equilibrium.
We assume it reacts.
What do you mean?
Like it's no longer.
Yeah, the only A we have is captured by the C. And how you would know how much you have is because you have this overall composition. So it'd be like it would be 75% B, right? So we have 2 B's for every A, okay? And so what is this one? This is AB, and this is B. So we have about equal amounts. If we're right here at 75%, we have chunks of AB and chunks of B in our solid. And it adds up to AB2, right? Because we're right at 75. Okay, so that's again the reacting systems we call it. So I think it'll become more clear. Let's do this one. Let's swap the order of these 2. This should make it more clear. So this is the mole fraction of silicon. So this is experimental data, the real phase diagram. So we have the mole fraction of silicon times 100%. So it's in percentage, 60%, 80% instead of 0.6. So way over here is 100% silicon. So we follow this vertical line all the way to the top. What do we have? We have the melting point of silicon. So you have pure silicon, been refined. Now you have 100% silicon in your little sample. It's going to have a melting point. So it looks like it's around 1400, maybe 1450. I don't know why it's not on there, but that's the melting point, Tm for silicon. Okay. Then way over here on the left, we have 0% silicon. It's 100% calcium. So this is calcium. So its melting point is 842. Does that make sense? You find that line. So this vertical line is all pure calcium. And we get up here, we have pure calcium's melting point, 842. But look at these. We have 3 different compounds that are various ratios of calcium and silicon. And we know that these 2 are pure compounds because they have their own independent melting points. So Ca2Si has a melting point of 1314, and CaSi 50-50 mixture is 1324. That's a detectable difference, right? This one is a little strange. It does what we call incongruent melting. Notice it's not a maximum. It doesn't go up to a maximum. It actually decomposes. So if we were to drop into, well, we'll do incongruent melting in a second. So does everybody understand that if there's a maximum up here, then we have a pure substance that we can isolate with its own pure melting point? So on this phase diagram, we have 4 substances that have 4 independent melting points. Now, what did you took melting points in organic. Why did you do that? To what? So does this phase diagram lend itself to that conclusion that if you have what was your test for purity? So you're doing a melting point in organic. You did some sort of synthesis. You put it in a little capillary tube and you test the melting point. What are the criteria you're looking for? Let's say you don't have a literature value. How would you determine if it was pure? Well, I mean, you need a literature value, but if it was impure, what would you see? Let's say the melting point was 225 and your compound was not pure. It melted before. Look at this phase diagram. The melting points of the pure substances are the maxima. So if I'm impure in either direction, the melting point drops, doesn't it? Yeah. So we're seeing that here. This is why we have those melting point apparatus, in organic chemistry. If you make a pure compound, in this case Ca2Si, and you put it in a really high temperature melting point apparatus that can go to 1300 C, and let's say you got a melting point at 1299. Okay. It didn't get to 1314, so it's not a pure compound. Okay. You don't necessarily know which side of that you're on, but it's not pure. Yeah. And it would also not have a sharp melting point. That's the second criterion for a good melting point in organic, is that it matches literature naturally, but also that it's a sharp melting. Like you see nothing, 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 and all of a sudden it's all liquid. It's very sharp. This lends itself to that too, because let's say we're right here and we're melting our calcium, dicalcium silicide, let's make that name, and we get to this point right here, we're going to start to see liquid and solid, and we keep raising the temperature, and right here it's all liquid. So we have this melting range, not a melting point. So this is when liquid shows up. And so we have some liquid, some solid in this range here. And then up here, we have all liquid. All your organic compounds would have similar phase diagrams, And so that's why you want a sharp melting point, because if you have a sharp melting point, you're on one of these vertical lines. So we're cruising up this line. If we've got a very pure substance, we're cruising, cruising, cruising. There's no liquid, no liquid, no liquid. We get right here, boom, it all melts. And then we have a sharp melting point, and we see that it matches literature, so we know what it is. If you don't have a literature value, you're just looking for the sharpest melting point. So you're controlling the temperature, and all of a sudden, it all melts. You're like, okay, good, we've got a pure substance. Okay, let's look at this really weird one. So here we have calcium disilicide. Okay. Now, what evidence would we ever have that substance is a thing? Well, let's say we're over here and we see, a solid phase and a solid phase. How do we know it's actually this line and not this one over here? Like, we need to make a decision, right? Because if this compound doesn't have a pure melting point, that line may not be there. Like, it may not actually exist as CaS2. We may have an equilibrium between pure silicon and the CaSi, the one-to-one compound, which does have a melting point. So the only evidence we would get to this is by looking at the grains in the solid. So down here, if we were to look at a micrograph, and we could see these various grains, and we were able to analyze them, we would have some silicon solid grains. And then if we were able to, I don't know, with Raman spectroscopy or some kind of, technique that would be sensitive to those, maybe X-ray fluorescence, where we could pick a beam and hit it with like X-ray, like in a scanning electron microscope. We hit it with the electron beam and we look at the X-rays that come out, and we might be able to determine that this one is CaSi2 solid. Okay. So if we had some sort of spectroscopic technique like scanning electron microscopy, you blast it with electrons, you knock out some core electrons, and you get the X-rays out, we will be able to see the ratio of silicon to calcium in that particular region in our microscopic slide. So we might say, yeah, we've got CaSi2 solid, but if we don't have a maximum here with an independent melting point, then we have what's called incongruent melting. So it decomposes here. So they've got kind of, I'm not sure if this little box right here is legitimate. But if it comes up here, I do know that it's very close to this eutectic blend, but right here at 1040, this calcium disilicide decomposes. I should put an arrow to that. Okay. And so then it starts to melt here. Let's go ahead and draw this liquid region here. So it starts to melt there and stops melting here. So this whole region of temperatures, we would see liquid. And so you see that that's not a pure substance, right? Now, in the solid phase, after it's down here, we're really rich in silicon, we would see some CaSi2 solid grains. But then when we try to raise the temperature, what we would see then is that this substance is not stable as an independent, purifiable substance with its high melting point. Okay, it does what we call incongruent melting. The same thing happens in the previous one. This is with sodium and potassium. In the solid phase, there's a compound called NaK, Na2K. It exists in the solid phase, but it doesn't have its own melting point. It decomposes at this temperature here at T3, and then you have a melting region from this point all the way up, depending on what your concentration is. So if I were to ask you which substance, like on this phase diagram, I could say, which of these substances, calcium, Ca2Si, CaSi, CaSi2, or silicon, there's 5 choices there, experiences incongruent melting. It's the one that doesn't have a maximum. So this one doesn't have a maximum like these other 4. And so it's not an isolatable pure substance. It only exists in the solid phase. It doesn't exist in this solid phase all the way up to a maximum melting point. So that's about as complicated as it gets for binary mixtures. And then we get into ternary phase diagrams. I just show you one just to show you what's called a tease plot. I don't know why it's called a tease plot. Maybe that's somebody's name. So a tease diagram. And these are kind of tricky to read. So if we put you in a data point right here, you got to figure out, how am I supposed to read this? Well, the one principle that you have from all of these is that all 3 components that are being plotted have to add up to 100%, okay? And so you find whatever data point you're at, you look at the axes, and if I have 2 choices, I can draw a line right here like that, which is parallel to this line down here, or I could draw a line like this, which is parallel to this axis. Okay, so what I want to do is I want to read the weight percent chromium. And so I'm going to find whatever point on that axis is 0. And I draw this line horizontal. If I want to draw the chromium concentration, it's horizontal to where 0 is. Because if it was right here, it would have 0% chromium. Okay, so then this point right here would be 10% chromium. This point is about 20% chromium. Okay, so we're going to mark through this one here. And then here's the 0 point for iron. And so I'm going to draw this line all the way up here, parallel to this line here for percent iron. And then I'm going to do the same thing for nickel. So this is the 0 point for nickel over here. And so I'm going to draw it parallel to that line. So here's the 3 lines that you have. This is the percent chromium, that's the percent iron, and that's the percent nickel. And they all add up to 100%. So 65, and then you got 80, and then 20. So add it all up. So that's how you read a tease diagram. And this is a way to plot 3 components. Now, as far as how you plot 4 components, I don't know. Okay. But we see the equilibrium lines. We see different, like this line right here is stainless steel. Okay. And we have these different regions, but this is the equilibrium between this phase of chromium plus iron and nickel. Here's this iron and nickel, gamma iron and nickel phase. And here's the equilibrium line between those 2. And so we've got all these different kinds of alloys of chromium, iron, and nickel. They all have different strengths. They all have different chemical reactivities. And so, you can clean your stainless steel knives and forks with bleach, but don't clean a Tesla with bleach. The stainless steel is a different grade. It's a different spot on this phase diagram. And it's not going to be it's going to be more reactive. In fact, they had, I think it was kind of I don't know if they fixed it, but they had some flash rust problems with the Tesla Cybertrucks. So, that's not what you want. You don't want to buy a stainless steel, exterior for a vehicle and then have it rust. Same with your appliances in your home. Stainless steel, refrigerator doors or stove or whatever, we want those to be chemically inert. And so that would be, I don't exactly know where the different grades of stainless steel fit on this diagram. That'd be something we could research, but some of these are going to be completely chemically unreactive. It's the iron that's the more reactive of the 3. And so a lot of them, they'll make the steel and then they'll pickle it. They'll put it in acid, and the iron is more soluble in the acid than the chromium or the nickel. So that's going to be a surface phenomenon. So on the surface, the iron is going to get dissolved out in the acid. And it's going to leave behind a chromium nickel coating that's depleted in iron. And so that's a way to make the surface much, much less reactive by sucking the iron out of the surface. And so that would be an acid treatment to prevent rust. So there's lots of things that you can do with these different materials. And, so I've seen 3-component phase diagrams like this. I've not seen anything with 4 components. I don't know how they would show that. But they'd probably just take slices of this. So if you had a 4th component coming out, you would have a certain concentration for that 4th component, and then you'd plot this for that concentration. And then if it was more concentrated in that component, you'd plot another triangle, just like we did for the PX phase diagram. Each one of those was a slice in temperature. So that's it for phase diagrams. We've covered a lot. Any questions about this one? Yes. Yeah. And so if you're looking at this, let's say this was a maximum. Where is my pen? Okay. So let's say this was, let's pretend that this isn't 1450, but that it comes over here and hits right there at like 1200, right? And so you might have a weird situation where silicon has a melting point at 1200, calcium at 840, but then you discover this mixture of silicon and calcium that has a 1300 melting point. You're like, that's weird. The pure substance is pure silicon is 1200, pure calcium is 840. Where did I get this 1300 melting point? Well, you've got a new substance. You've got a new compound that you've made. That's a stable compound. It has a stable melting point. Yeah. And can be purified. Yes, but these are metallic bonds in these cases, and that's a little confusing because we sort of had these hard categories of covalent bonds, ionic bonds, and metallic bonds. Okay, and and that's what we teach in freshman chemistry. But this may be something, yeah, it's I don't know that it may be a covalent substance of Ca2Si. It is purifiable and it does have an independent melting point. But in terms of the bonding, that I don't really know. I haven't really thought about that. So that's a good question. Yeah. Because it seems a little strange that you would have, but there's a lot of weird stuff that happens, like sulfur. The molecular structure for sulfur is S8. Why? Why not S6? Why not S4? Are there substances in sulfur that might have S4, like a solid phase, and then you change the pressure and it becomes S8, or vice versa? Like water has four different ice structures, 1 through 5, but we're missing number 3, something like that. Maybe there's ice 6, I don't know. But that's weird too. Yeah, so nature's a weird one. Yeah. But in this case, we definitely don't have an independent substance, calcium disilicide, except in the solid phase. It doesn't go up and have its own independent melting point. And the best way I can describe incongruent melting is a decomposition, which kind of makes sense. The compound is solid, but then once it reaches a certain temperature, it just decomposes and begins to produce a liquid phase. Okay. Yeah, I think that's it.